Good evening, everyone, and welcome to another Scottish Centre Arnets talk. And it's very nice to see that we have guests on. Just as a way of an introduction, my name is Gary Johnston. I'm the chair of the Scottish Centre Committee for the Royal Meteorological Society. And we have these talks regularly on a monthly basis, and it's a free talk. You're quite happy that people join in and participate, and we are trying to encourage people to become members of RMET. It's not essential, but we would like to see people become members. It's a very worthwhile organisation. If you've got an interest in meteorology or the weather, or indeed in a greener environment and the way things are going just now with climate change, you're more than welcome to join the society. Tonight, we would ask that, if possible, you use a Chrome browser, and if you are having problems in listening or hearing at all, then the best solution is probably to close your browser and start again. We have had one or two people in the past saying it's difficult to hear myself or the speaker or to read what is happening. But if you are having problems, just try and be patient and log out and log back in again with the browser. You will see on the right hand side of the screen there is a whiteboard, and during the lecture tonight, the talk tonight, if you have any questions, could I ask that you just put them onto the screen, onto the whiteboard, and we will ask the speaker if she could address these after the talk is finished. If there is something specific that refers to a particular slide, if you could possibly take a note of what that slide is, so we can maybe refer back to it when your question is being asked. Now, in saying that, I would just like to introduce our speaker tonight, and it's somebody that I'm particularly keen to hear, because this is actually my profession as well, as in architecture and planning. So I would like you all to welcome Professor Sue Roaf from Heriot-Watt University, who is going to speak to us tonight on the subject of extreme design, buildings for a future climate. So, Sue, it's very nice to see you, and welcome to the Scottish Centre Arnets. And I will now hand over to you to give us your presentation. Thank you.
Thanks very much indeed. I'm just wondering, if I disappear too, does that make the screen larger?
It doesn't actually, so you're probably better just to stay on.
Okay, now I want to talk to you about thermal comfort. It sounds a pretty boring subject, but in fact, it is a critical factor in the climate change equations. And I'll explain to you why that is. Apart from being a nephophile myself, or a cloud lover, I'm also very interested in comfort clouds, and I'll explain what they are during the course of the lecture. Comfort is very complex, just like clouds. Comfort is what we seek to avoid being uncomfortable. And we do this with a thermoregulatory system, which is designed to keep our core temperature at around 37 degrees centigrade, a safe working temperature. Now, we do that with involuntary actions, and we do it with voluntary actions as well. The involuntary ones, like sweating and shivering, involve body tissues and skin. And the voluntary actions we do by changing postures, clothing, activity, environmental controls, and locations. And you can see from these thermal images of a man, a woman, and a child that actually the physiology of men and women is very different. And so that's another factor too. The yellow there is subcutaneous fat, which I'll go on to touch on again. Comfort varies infinitely with age, sex, health, weight, shape. I think I've studied 64 different variables for that. And it also very much changes with the way we interact with the world around us in terms of the physics of our environment. Now, we use conduction when we touch a surface, a floor or a chair or a bed. We will conduct, gain or lose heat. Convection is air moving around the body, which it's continually doing, changing our physics. Radiation from surfaces, from the sun. And we exchange quite a lot of heat with the environment through respiration and moisture. We breathe out and in, which with the large lung capacity we have exchanges a lot of heat with the environment. And of course, then we sweat and evaporate. That's evaporative cooling from the skin. Now, the involuntary actions of the body work without us knowing to restore comfort. And you can see them circled in red here and linked by the central nervous system, shivering, sweating, which occur at different temperatures in the body and the skin. And now we have, if you look here at the temperatures, the question is, at what temperature do these changes happen? Here we see on the right there, the thermoneutral zone. Now, this is a physiological state in which a naked resting body is able to maintain its core temperature simply by the ticking over of its metabolism, the basal metabolism. It doesn't need to sweat, it doesn't need to shiver. And typically when it was first identified, these temperatures might surprise you. You think of yourself in a hammock on holiday by the pool, and it's blissfully neither too cold or too warm. You're in your togs. What sort of temperatures are you looking at? In fact, the earliest identification was about 28 centigrade as the lower end of the thermoneutral zone, and going up to 32, 33 here. And around about 30, people start sweating, and gradually the sweat increases as you try and lose more and more. So between about 35. So now we see it's roughly between 26 and about 35. That's the temperatures that your body is most comfortable at. And what's really interesting is that those are the sorts of temperatures that we evolved from as Homo sapiens grew up on the steppe lands of East Africa. These are the temperatures that they would have occupied before the migrations 200,000 years ago, as we moved northwards, westwards into different climates. So below that thermoneutral zone, the body starts generating more heat to keep that core temperature at 37. And then gradually, as it gets colder, you start more visibly shivering. So we've got that on that side. And interestingly, if you put a thermometer between yourself and your bedclothes, it'll be somewhere, the temperature will be somewhere around 30. That's the core of our thermoneutral zone. That's when we're most thermally lazy, really. Voluntary actions also include here activity changes, clothing changes. And you can see when the early research on clothing was done, in 1941, clo units were invented. And the standard person with their clothing was seen to be the ordinary businessman in his business suit in the office. He was the person that we were most concerned with. And that was one clo is a man in a standard business suit in the office. And then it goes up, of course, 0.5 in your beachwear and 3.5, 4.5. We've seen studies in Nepal where they're getting on up to 5 klo units they're wearing. And then, of course, we've got activity. So here we have a resting body will be generating 80 watts of heat. If you're just sitting down, it will be maybe 100. If you're doing filing and actively moving around the office, 144. And if you're really running hard, that's about 400, 500 watts the body is producing. And how's it producing it? It's basically turning the calories we eat into heat. So that's why if you get an international cyclist or an athlete, they know exactly how many calories they have to eat in order to be able to cycle so far or run so fast. So it's a fairly developed science, that one. There are so many variables. It really is impossible to predict comfort of an individual or a typical individual accurately. And here you can see the globe temperature that people live in, and that's their metabolic rate. So as the metabolic rate increases, generating more heat, you can be quite comfortable with much lower klo units and clothing. And here you can see that your thermoneutral zone will vary according to how fat you are. The fatter you are, the more comfortable you are in lower temperatures, because you've got your own fatty overcoat you're wearing around with you all the time. Then you put the real clothing on. If you're wearing a klo unit, your thermoneutral zone will be very different than if you're naked. And your energy activity, what activities you're doing, how much you're eating will affect your thermoneutral zone, as will your age. And it narrows a lot the older you get, and we're not quite sure about the younger end, but you can see that all of these variables go into deciding. I mean, how often have you and your husband or your wife had an argument about turn that thermostat down? Or maybe in the office, somebody says, I'm freezing, the sort of the thin lady by the drafty door, or the plump lady, you know, over by the all the machines in the corner of the office. They'll have very different comfort temperatures. And we've got another way in which we adapt our environments. We can use environmental controls. And in your house, you'll have many different ways of changing your comfort temperature. You can put blinds down to stop the sun coming in, open the window for fresh air. You can do some activity, turn the fire on, have a hot drink or a cool drink, put more or less clothes on, sit under a blanket while you're watching television. That's the environmental controls around you. Turn on a fan. And of course, what people are doing now in more extreme climates and extreme temperatures is they are exploiting the thermal landscapes of their buildings. So at night, I know a number of people who will move downstairs from their upstairs bedroom to sleep downstairs in the cooler room during an extreme heat wave. So that buildings are thermally landscaped, just as our planet is. So many societies will go up to the mountains in the heat of the summer, or down to the seaside, or if you want a real sensual temperature thrill, you might take yourself to the hot baths in Iceland, or take yourself skiing to make yourself the frisson of skiing in the cold air, and then going and standing in front of the warm radiant fire because of après ski. We have a number of of systems in our bodies to reward us for thermal sensations as well. So that's the involuntary and the voluntary actions we can use to adapt to those places we occupy. And so you say, well, actually, what temperature, how can I decide if there is no one comfort temperature? How can I decide, make design decisions on what systems I need, working from that? Well, funnily enough, around the world, like I say, that the thermoregulatory system, whether you're an Eskimo or an Inuit or somebody living down in the tropics, you have the same thermoregulatory system. You have the same need to keep that core temperature of 37 the same. Now, here's data from Pakistan, and look at the temperatures at the bottom. This is percentage of people using environmental controls. And you'll see that around 20 degrees centigrade, the fans are going on. The heaters are being all turned off by 25. The windows are being opened, again, above 20. And, the metabolic rate is the activities are fairly constant. This is in offices in Pakistan. And again, here, that's sort of for 18 to 35. And here again, we've got 18 to 35. You start sweating more. You need more air to get rid of the sweat. You take off more clothes. And you can see on the right here, this is the percentage of sweat on the skin from 30. That's the center of your thermoneutral zone. So you've got more sweat on the skin if you don't move it with air. And if you do move it with air, then that evaporatively cools the skin. So again, from 30, without air movement, you've got far fewer people who are comfortable or cool than with air movement, because that sweat evaporation is cooling the skin. So we have got some indications of temperature ranges for comfort. Now, my doctorate was on the wind catchers of Yazd in Iran. Comfort is a cultural construct related to climate, and people in their everyday lives have thermal lifestyles. So here in Yazd, where you've got temperatures outside, 38, 40 above the roofs of the old town, you've got courtyards, you've got summer rooms, you've got basements, and people sleep on the roof. And here you can see them. They move from the hotter courtyard onto the roof, where with clear skies beneath the stars, they sleep underneath eiderdowns, and the temperatures go down there. This is 3 different housewives in different houses. As soon as the sun rises in the morning, bang, they're off downstairs because it gets too hot quite quickly on the roof. And they're pottering around in the courtyard, cooking lunch, cleaning, washing, doing domestic chores. And at around 12 o'clock, it's getting pretty warm then, 37. And the whole family, the men will come back from the bazaar or work. They go down into the basement where they have a lovely sleep. They have a big lunch, sleep it off in the coolth of the basement. And then as the sun leaves the courtyard, the evening breeze rises up. They'll come up, spread water on the courtyard, bang, straight up there. And you say, well, this is nearly 10 degrees centigrade difference that they're changing here. But this is well-known customary temperatures. So this is safe thermal behavior. They know what it's going to be. The human body is rather like an energy battery. So you will deplete the energy if you go out in the cold, and then you'll go back inside to top up your energy and the heat in your body. And if it's on a safe routine, then it's perfectly, it's how people live in non-air conditioned buildings. But closer to home, if we look in England, this is over 400 data lines between November and January. So this is winter data. And we're looking at people in houses in England across a day. And some people are at 10 degrees centigrade, 11 degrees centigrade. Some people are at 26. So how do you work out what's happening? All these different houses and different lifestyles. Well, what Hübner et al. Did was they reduced it to what Fergus calls thermal heartbeats. So the main patterns in all that data was that, let's take in winter, family cluster number 1, they keep the heating on all day. And it's pretty low. It's only around about 19, but it's a very steady temperature. And then you get some people who at night in the bedroom will, the temperature goes right down, but they get up at 7 o'clock in the morning, turn the heating on, they go out to work or to school, and they come back around about 5 o'clock, and bang, the heating goes back on, or it's set to come back on. So you have a warm evening there. And there's various iterations of that. So these are the sort of thermal heartbeats of different lifestyles, thermal lifestyles in ordinary houses. And have a think about in your own home, the thermal lifestyles you lead. Anybody who's taught in Edinburgh or Scotland will know that there can be deep snow and frost on the ground, and some people who've come from hot countries will wear their anoraks into the lessons, and then you'll get a lad from Inverness who'll come in with t-shirt and shorts or t-shirt and jeans. They're accustomed to different thermal lifestyles. How do you find out about what comfort temperatures are? Well, you can start off by reading our books. We've got a simple introduction into adaptive thermal comfort, and then we've got the complex, more sort of techie, detailed researcher's book there. And I'm just finishing the third one in this trilogy, is How to Design a Comfortable Building. Now, there are 2 ways in which comfort is researched. One has traditionally been in the laboratory, and this is the Hevac Industry approach. The Hevac Industry that uses the outputs of laboratory experiments to develop steady state calculations, or a heat balance method. The best one known as PMV, developed by Olefanger in Denmark. This work has been historically done Northern Europe, America. So what you do is you get people in the laboratory to see their respiration rates, etc. Or you get, most of this work is done by young college-age male students. Much of it was done in the 50s, 60s, 70s with small cohorts of non-diverse subjects typically. But from all these laboratory experiments, they worked out that human comfort is reduced to 4 basic physical parameters: humidity, right? Air temperature, air speed, and radiant temperature. And then they add 2 parameters which are assumed, which is how much clothing are they going to be wearing and what's their metabolic rate. So they put all of that into a bag, shake it out, and come out with a comfort temperature. That's the laboratory approach. And out of that, they have got, it's marvelous. We see quite a lot of research where they come out with comfort temperatures to 2 decimal points, which is marvelous. But the Hevac Industry, who write the regulations in America and largely in the UK as well, make their money by putting equipment into buildings, okay? So, for instance, using PMV standards, you can have very narrow limits. And also within the regulations and the international standards, they introduce categories like A, B, C. So do you want an office that's an A office? So in summer, if it's going to be an A office, in your office, you know, your big office room full of, you know, multitasking desk people, they recommend in the European standards a temperature of 24.5 plus or minus 0.5 of a degree centigrade, right? So that's 1 degree around 24.5 for summer. So it's 23.5, sorry, it's 24 to 25. Well, anybody who's been in a room where you've got a temperature, a large room with many people in it, where you have got so little thermal difference across a space, I'd love to know the address of that building so we could come and investigate that phenomenon. And that's an A-class office. So, you know, ambitious developers are pushed to high-end offices with that sort of thermal limit. Then you've got a B, but you've got the C standard, which is 24.5 plus or minus 2.5. So that's plus or minus, so 27 to 22, which means that you can open a window, yeah? So the international standards are pushing buildings in the direction of very tight thermal control. That's EN ISO 7730. Narrow comfort zones need much more heating and ventilating. And in a first-class office, in winter, obviously, it's different, but in a first-class office, you've got to maintain 21 to 25 over the year. Such narrow comfort zones mean you need super efficient air conditioning and lots of it. So you'll need more expensive Hevac and you need much more of it. So people are continually being pushed to very highly mechanized buildings through the regulations and the standards. The third class naturally ventilated buildings, permissible under the international standards, is something like 19 to 27 C over the year. Well, we've seen that people can be quite comfortable, but we'll look at this a bit later too. So they're pushing developers away from naturally ventilated buildings. And if you see in the United States of America, ASHRAE, the American Society of Heating and Ventilating, Refrigeration and Air Conditioning Industries, these are the temperatures in the comfort zones from America from 1941 to 2009 in Japan and the USA. So in 1941, 17 was perfectly acceptable in winter, 17 to 22. By 2009, even after the Kyoto Protocol, that was 22 to 24. Well, that's pushing up. For every degree centigrade you increase it, you're using 10% more energy to heat or cool the space. So that's pushing up the energy use enormously. Japan is much more sensible, much more stable. And you see after the Kyoto Protocol, they actually dropped the required temperatures in winter. Here in summer, in 1941, 24 to 27 was perfectly adequate. But gradually over time, the ASHRAE has pushed it down and down and down and narrowed it. Because you see, if you narrow it, you have to have much better equipment, more expensive equipment. So here we're 24 to 26, I think, in summer. So you can see the trend in the laboratory derived, and it's often fairly weak laboratory research, is used as the basis to push these international standards. There is the other way to work out how comfortable people are going to be. You actually ask them how they feel in the buildings they live and work in. And then sometimes you ask them how would they prefer to feel. Sometimes it doesn't actually correlate. They'll say they're very hot, and then they'll say they want it hotter or something like that. But these are two scales. The ASHRAE scale, it's a 7-point scale, basically, from cold to hot, with neutral in ASHRAE in America as naught, and comfortable on the UK Bedford scale, much too warm, much too cool. You know, Britain led the world in comfort research in the 20th century, early 20th century, not least because they had the biggest empire. And you found that if you put people in the tropics in bearskins and woolen uniforms, they had a tendency to fall over on the parade ground, which is inconvenient. Or so a lot of research went around military comfort or survival in military situations or in industrial ones. A lot of the work was done in deep mines in South Africa, 2-mile deep mines, where they put people down to work all 8-hour shifts in 40, 50, 60 degrees centigrade. And when they started dying, they decided they needed to know more about comfort. Now, the adaptive thermal comfort model was pioneered in the UK and based on the work of Bedford in the 30s in factories, and then taken over by Charles Webb, who started to ask people around the world in very well-designed comfort surveys how they felt. Were they comfortable or not on the Bedford scale? Thermal comfort has been defined as that state of mind which expresses satisfaction with the thermal environment. And what Charles Webb found was that people, if you look, here's the mean globe temperature of the spaces they were in, from 38 to 16, and that's the mean comfort vote. So here's neutral. And people were comfortable in Baghdad and Iraq and India at 32, 34, 36, even 38. And in Britain, they're comfortable at 20 to 24. So you see, as Mike Humphreys pointed out, as early as 1970, actually, the neutral or comfort temperature correlates completely with the outdoor air temperature. So people are comfortable in those temperatures. They learn to adapt to those temperatures they normally occupy. And that's the adaptive principle. People are comfortable at the temperatures they normally occupy, and if they're uncomfortable, they act to restore their comfort because they have to keep that core temperature thermally safe. And Fergus Nichol, Mike Humphreys was head of human factors at the BRE. Fergus Nichol worked with him and then at the Medical Research Council and came up with this lovely diagram of the very dynamic feedback systems that are going on all the time, subconsciously mainly, for all of us, keeping us thermally comfortable. And now, in an adaptive thermal comfort study, you study real people in real buildings. And you note the use of controls like windows, blinds, so on. You measure the environment, what temperature, humidity, airspeed. You note the clothing they're wearing. And you ask them, how are they feeling? And through, actually, it's now hundreds of thousands of data sets we have from around the world, temperatures around the world. You can then plot it and use statistics to predict when 9 out of 10 people or 8 out of 10 people are going to be satisfied. Again, following that same principle that people adapt to those temperatures they normally occupy. And this is work done in Berkeley, California, where they've done some fantastic work, and also Gail Brager in Berkeley and Richard Didier in Australia. If you're working in an air-conditioned building, you will adapt observed field base and predicted by the laboratory. You adapt to those temperatures that are predicted by the laboratory. If you go into a naturally ventilated building, the laboratory predictions will give you a very different picture of the indoor comfort temperatures, because people adapt to those temperatures that the existing PMV, the steady state calculations, are really inaccurate for the anything that's naturally ventilated. They predict that you're going to need a higher temperature to be warmer in winter and a lower temperature in summer. So that means you need air conditioning, more air conditioning there, and more heating there. So this is the climate reality. Indoor comfort temperatures are directly related to outdoor temperatures, and using statistics, one can develop algorithms that are then fed into controls or used to predict roughly an adaptive model for what temperatures people will be comfortable at. And for instance, in Holland now, they have an adaptive regulation, which basically says between 18 degrees centigrade and 28 degrees centigrade, that's a fairly safe thermal space. So you really don't need to worry unless it's rapidly changing. If it's a stable temperature in summer at 27 and in winter at 18, you can use other adaptive, what they call personal comfort systems. Put on another jumper, foot warmers, fans on the desk in summer, and so on. And here's where we're getting into the land of the comfort clouds. So when you statistically reduce those vast data sets to regression lines, you're taking away the richness of what you can find out from the spreads of data. So here we have naturally ventilated buildings, globe temperatures, and we assume that if people are living in these temperatures, they are acceptable to them. And you can see the comfort vote. You notice this kink. So people are starting to heat here, and then it's free running. It's neither heated nor cooled above these sort of, that's the outdoor temperature. And this is indoor globe temperature. So that's the indoor comfort temperature against the outdoor temperature. And you can see these are 5,000 data from surveys in Aberdeen and Oxford. So you'll have people in the north of Scotland with the comfort vote, that's getting too hot here, indoor temperatures. And yet some people down here, some people are perfectly comfortable in those temperatures. So it may be that the Oxford population is very different from the Aberdeen population in terms of their comfort vote for these indoor globe temperatures. So we have the black dots are too cold and the black triangles are too hot. So it's a very mixed bag, and a lot of it will depend on the individuals, how their size, their shape, their predilections. Now, different adaptive opportunities shown in these graphs show that if you have an air-conditioned office, right, indoor globe temperature 20 to 25, that's extremely stable, and that's the outdoor temperatures. So it doesn't matter if it's naught outside, it's still that, and if it's 25 outside. Now, this is the problem with that, is that, like I said, for every degree centigrade that you have to cool it in summer or heat it in winter is another 10% on your energy consumption. So that's fine. You can keep indoor temperatures like that if you can afford the energy, and if the planet can afford the energy, because air conditioning systems and heating and cooling systems are responsible for nearly 40% of all the greenhouse gas emissions from the on this planet. So that type of comfort comes at a huge expense to the planet. So naturally ventilated offices, the use of heating, is the heating on or off? So here we've got that 15 again, it's off, and below 15 outdoor air temperature, it's on. And that's the heated part. Now look, if we look at naturally ventilated buildings where you've got fans running, the indoor globe temperature is what is occupied by these people. And so fans, they are running at all sorts of different temperatures, outdoor temperatures, but they tend to be here as the temperature reaches at 25. There's, large number of fans are going on here, but in other areas not. So this might be Oxford versus Aberdeen, I don't know. And windows open and closed. So again, we've got outdoor air temperatures above 10 and indoor temperatures above 20. We've got a fairly universal spread of people opening windows. And like every Bavarian housewife, I believe that one of the founders of the passive house movement was threatened with divorce because he made his wife, a good Bavarian housewife, stop opening the bedroom windows to air the bedrooms every morning. She refused, but I think eventually it was resolved. People can open windows at any temperature, and you'll do that in your own home if you want a bit of fresh air. So with air-conditioned buildings, you've got very narrow indoor temperatures, and here you can go from 30 to 17, 18, with quite a variety, and people not reporting discomfort. But when we said that comfort is cultural, we've got some wonderful data, 4,700 surveys, different surveys from France, Portugal, Sweden, and UK. And a cloud of points is formed. This is Fergus's comfort clouds. And each point includes dimensions such as, there'll be, in each point, you'll have a lot of detail on air movement, clothing, humidity. So Fergus spends a lot of time playing with his data. But what's really interesting is the cultural differences. So if you see here, this is Sweden. In Sweden, where they're largely fixed windows with heat pumps, year-round air conditioning, the temperatures are invariably 20, 21, 22 to 25, because they are fully conditioned. I mean, that was a very cold, Sweden is a much colder climate. So they have now got a fully conditioned culture. Let's take another one, France. France is rather good. It's bimodal. In winter, they heat their buildings, and in summer, they throw the windows open. And here we have a shape. So the hotter it gets, the higher the comfort temperatures in it and naturally ventilated buildings. And here we have Portugal, which is a hotter country still than France, but they don't do heating very much at all. They just they rely on naturally ventilated buildings. And of course, in the old days, they'd have a small heater under a table with a blanket over it. But actually, people in winter can get quite cold in Portuguese traditional houses. But that's just fully naturally ventilated. And in the UK, it's absolute barn pot case. You can't tell what's happening. It's neither, but you've got that naturally ventilated Portugal, bimodal France, and fully air-conditioned Sweden. And if you go up looking in hotter countries, this is work we did in the 90s in Pakistan. We've got Saidu Sharif up in Khyber Pakhtunkhwa. We've got Peshawar on the plains above Islamabad. We have Multan, which is a continental desert climate. We have Karachi, which is on the Indian Ocean, a maritime climate. And we have Quetta, which is the highest of them all and the coldest of them all. And so you see, if we take Quetta here, that's the temperatures over the year in Quetta. And then let's take, you see, this is the maritime climate, Karachi, much lower variation. And then Multan, we get the full continental climate, which is shown in the temperatures and reflected in the shape of thermal comfort in Pakistan. So we take Multan, which is the continental desert climate. People are quite comfortable or live in temperatures, they seem to be quite outliers, but going up 35, 40. Whereas in Quetta, which is very high, up by the Afghan border, we've got people living in temperatures of 10 and so on. Saidu Sharif, which is the montane climate, is cold, but less variation than Quetta. So you see, the temperatures people occupy are dictated by the climate. And if you look at the, you very often get by the scientists or the laboratory researchers, they say, who've been working all their lives in a Danish laboratory or somewhere. And they say, but are they really comfortable? They couldn't possibly be comfortable at those temperatures because they've probably lived in that sort of Swedish air-conditioned environment their entire lives. So they cannot sensually or intellectually comprehend that people have very different thermal cultures. And so here in Pakistan, that, we're getting above 40. People are hot. They are living in hot conditions there. And people get cold in Quetta. And then you've got, say, a band here of sort of general responses. But for a range between 10 and 40, say, you've got the comfort votes. There's relatively surprisingly little at each end there. But now this is important. This is the link between comfort and climate. So you go to Multan, which is the desert continental climate, and you've got 80% of people reporting themselves as really comfortable between 22.5 and 35. Now, if we go to Saidu Sharif, the montane climate, there's 80% of the people who are comfortable between 15 and 30. So while the average data will show you a histogram a bit like that, in reality, every city is different. So Glasgow will be very different from Edinburgh in terms of their thermal responses. Inverness will be very different from Aberdeen and Oxford or London. It's because people have adapted using involuntary and voluntary acclimatization and adaptation practices and cultures to adapt to those temperatures they normally occupy. And anybody who's an architect, this is the work of Victor Olga in the 40s, who decided the comfort zone really, with a meter of some good wind speeds, 32, and then with a bit of radiant heating, you 20 to 30, 18 to 32, I'd probably push it to. And people, the Americans love humidity for some reason, but any of the comfort surveys that we have been done, tens of thousands, hundreds of thousands of data points show that actually humidity is not the problem, temperature is the problem. So indoor air temperatures here going up and relative humidities here, and the comfort vote, people are perfectly comfortable 35, say 18 to 35, regardless of the humidity, because it is almost impossible. If you say to somebody, what humidity is it in this room, they will inevitably get it wrong. And one of my PhD students in Dammam on the Gulf did this quite extensively. And people in the Gulf, where you're supposed to have this hugely high humidity, really had no idea what humidity they were living in. So these people who say, oh, you're going to die when the temperature gets to 35 and it's 100% relative humidity. Well, it's never 100% relative humidity for long. It's like people can work in yurts in Siberia herding the sheep for an hour in minus 20, but then they go back into the tent and warm up by the fire. You've got a lot of leeway in how much time you can spend in the most extreme conditions. So sometimes you hear an awful lot of guff being spoken on the BBC. Look, head in the clouds, thermal comfort conclusions. The close relationship between the data from one place and another shows that between subjects in climatically similar places, there are underlying orders for the data. You know, people turn on fans typically, start to sweat at the same time, anywhere in the world. And there's an order that you can use to design free-running buildings. The differences in comfort between different cities in Pakistan and other parts of the world suggest that comfort is based on climate rather than country. So what you have to do is you have to this is where if you want to design for a new climate, first thing you do is you go and look at the vernacular architecture of that place, because that will tell you how much wind they want, how much mass you need, what orientation is best, etc., etc. Comfort is clearly decided not just by the indoor environment, but also the outdoor climate, the culture and lifestyles of the people in a place, and the context, the socioeconomic, the political context too, as we saw with those different comfort zones. And we will find now, as Britain, what we have now as a phenomenon is the disappearing middle classes. So we will find that people's comfort envelopes widen because they simply can't afford to sit in unnecessarily high temperatures in winter or unnecessarily low ones in summer. Comfort clouds have helped us understand the imprecision of the interrelationships. And basically, we believe that the steady state, narrow comfort standards really only apply to high-end, fully air-conditioned buildings. If you've got the big move now is to mix mode buildings, where you can have them run for as much of the year as possible just on local natural energy. And for that, you have to use adaptive thermal comfort standards. What's that last one? And this isn't a backward step. This is going to provide inspiration for really good designers It's going to be liberating not to be tied down to the diktats of an engineering profession who really are basing the move to ever tighter comfort zones on very poor science. So look, my question here is, why should people in Sweden who are writing the international comfort standards dictate what temperatures people ought to occupy in Portugal or Pakistan, where they have no understanding of the conditions that people are comfortable in? But that's what's happened. This is the international style of architecture, which is why in the Gulf you get billions of dollars of wasted money with overcooled buildings. And you get that around the world anyway. Now, here are the comfort. You see, we've got these comfort clouds. Darwin in Australia, Pakistan. These are the English clouds. Tokyo, Shanghai. They get very cold in Shanghai. Melbourne. I mean, any city can have its own comfort cloud, which will help designers understand how to design. Now, listen, why does comfort matter? Because the future is different. We've gone up this sort of dead end. There is no future in a heating world for shut off, fully enclosed buildings. We have to find a way of making a world that can run on clean, renewable, local energy, because otherwise very many of us won't survive. The world is changing so fast. Look at London in 1995. Look at Las Vegas. Look at Sheikh Zayed Road, Dubai, 1991. The Hilton Hotel complex. 30 years later, this is what it looks like. Each of those buildings is like one of these tall buildings here can use as much energy as a town in Africa or a small city in Africa, some of these. That's the scale of the problem. And what is really fairly dispiriting is that we've known from the 90s. This is work by Bill Bordas in the early 1990s. The Econ 19 study looking at the energy used in buildings. These are simple, traditional, naturally ventilated high mass buildings here. Good practice and typical. These are 1960s naturally ventilated, lighter weight buildings, but still naturally ventilated here. This is standard air conditioned buildings in the UK in the early 1990s. And these are high-end, big glass towers. Simply, so in order to enable them to be, they use much more energy, they cost much more to run, and they emit so much more CO2. So a really high-end tower, big glass tower, will emit, 4 or 5 times more to do the same work per meter square floored. And this, every time you go up another floor, you're using more energy to just build a square meter too. I mean, I've been born in 1952 from a world of ordinary buildings. And then suddenly by the 60s and the 70s, with the development of lifts and air conditioning and the pushing, these building regulations, and here's another very good article showing how the building regulations are pushing into ever more mechanized buildings. But this is a dead end and it's killing the planet. And yet we get all of these green rating schemes. This is the American Green LEED rating scheme. These are all platinum buildings. You cannot get a platinum LEED rating, or you could not when it was started, without having full centralized air conditioning and all the windows closed. And I think that is shameful. In Britain, we have Briem Estimates. The designers say, oh, it's going to use this much gas, this much electricity as they do the models. And then we have sort of more advanced models, design estimates. That's a rating scheme by the BRE. By the way, the current building regulation committee is now chaired by the head of the BRE Buildings Division. And they peddle these green rating schemes, which are completely erroneous or produce spurious results. Oh, it's going to only use this much. In reality, you saw the Econ 19 benchmark for good practice and typical for high-end buildings. I think this is the Gherkin. And actually, it's not even good practice they're producing. That the entire, and they're still building these hundreds of glass towers in London, not least because the people who decide on them in the planning committees in London, some of them are even developers with property interests in the London property market, and they're allowed to sit on the planning committees that make these decisions. Now, look, this is a book we brought out in 2004 and 2009, just showing with global temperature changes, 1 degree, 2 degree, 3 degree, 4 degree, buildings fail. So we have to increase building resilience, and the high energy solutions are no longer affordable, even where we are now, 1.5 degrees centigrade. Communities fail, and we've seen that. The Arab Spring was the price of bread after the 2010 heat wave in Russia, triggered the Libyan Arab Spring, which then spread across the Middle East. Communities, we have to refunctionalize communities, because in the end, the only thing that will save you is a safe community. Building infrastructures are failing everywhere. This is Oman. It could be Scotland. We have to fortify and make more resilient our cities and our infrastructures. And the system capacity is exceeded. Inequality in its societies is magnified, and that gets to tribal again. And capacity planning and resource allocation means that people go around. This is Lake Mead, which is already hovering around the 1,000-foot water line, below which you can no longer generate. And Las Vegas and Nevada are dependent on this water. Even in 2008, they were opening 7 new golf courses in in Las Vegas, while Lake Mead was plunging to unsustainable limits. They weren't willing to listen before. People are much more willing to listen when extreme weather events affect themselves. Floods in Germany, the heat dome in Northwest Pacific in 2021, Texas, the ice storm in February the 16th, cutting out electricity across a whole lot of Houston. So you've got freezing buildings and you've got no grid, and that's another thing that's happening too. And something we've learned with the pandemic, nobody is safe until everybody's safe. And the scandal is that 40% of global electricity emissions come from some buildings. They don't come from all buildings. They don't come from these buildings. They come from these buildings, occupied by these people, the top 20%, the top 10%, the top 5% in the world, right? And here we have the phenomenon of the disappearing middle classes, where incomes that's the top 20%, right? May keep their head above water as we go forward into global economic crisis again. This is what happened in 2010, and this will be even worse now. So the bottom 80%, they can't afford. This was in 2016, people who cannot afford to keep their home adequately warm in Europe. In Bulgaria, 40%. The UK, 6.1%. Well, that's going to be what, 30–40% of homes now, with the doubling and the tripling of energy costs. Comfort is extraordinarily important to the building of resilient societies. Here we have the 2003 heat wave. That was an outlier. 72,000 people died across Europe in that heat wave. By 2050, that is going to be a very cool summer. Comfort clouds and climate. At the heart of the way forward to resilience in the built environment is to mandate that all buildings must be run for as much of the year, the day, the season as possible on free local energy. They need to avoid overheating and provide thermally safe spaces. They need opening windows. They need very good, locally appropriate climatic design. All buildings should now be designed for local climates using adaptive thermal comfort standards. For more information, do see some of our books on adapting buildings and cities for climate change, benchmarks for sustainable buildings, eco-house design, and energy efficient building, which is, we wrote this in the 90s. It's basically passive house, but that's 20th century thinking. The noughties was about sustainability, but nobody knows what that is anyway. It's a bit of a fudge. The future has got to be about resilience, about how to keep people safe when the lights go out. And please, if you're interested in this, we've got a whole one-day event on it in London. Comfort at the Extremes. Have a look at that. And if you want to join our network for comfort and energy use in buildings, contact Fergus. And here's his email, and just say, put me on the list. We've got about 800 people around the world in that network. The future is very different, and we have to wake up now and count the coffins. Thank you very much. Hi, Gary. Was that all right?
Thank you. There we are. Sorry, I had a bit of trouble getting on there, Sue. Thank you very much.
I can't hear you.
Oh, we have got the... Should be able to hear me. Can you hear me okay?
Can't hear you.
All right, my microphone is on. I don't know if anyone else can hear me there. Can you hear me now, Sue? Oh, dear. Well, microphone is on here, and it's certainly saying I'm broadcasting. So, Sue, I think it's at your end that I'm getting messages. Yeah.
Gary, we can't hear you.
I can hear you.
Yeah, thanks, Richard. Sue, I think it's at your end. Alan, if you can maybe send just a message to Sue that people can hear me okay. So I think she needs to put her speaker on at her end. Okay. Well, I'm going to continue. So there are some questions that are there. I hope you can hear me now. It seems that other people can hear me okay. And obviously, I want to thank you very much for your talk. It's something that you're obviously very passionate about. There are a couple of questions. So if you would like to put your microphone back on, the first question is from Chris at the University of Edinburgh. Now, I will let you read it there, but basically, you've mentioned naturally ventilated offices, which are presumably working to accommodate high numbers of people, computers, etc. What size of effect do you think that the transition to a home working, where these heat sources are more greatly dissipated, will have on the cooling and heating demands? Sorry, Sue, we're just not hearing you at all. I don't know if anyone behind the demo can maybe try and sort this, please, because it appears that it's at Sue's end. She can't hear, or we can't hear her. Nope. Sue, I presume you can't hear us at all, Sue. I'm just not hearing Sue at all, which is really disappointing because.
Okay, wait a minute. I'm going to go back into this one.
There you are. We can hear you now. Can you hear me okay?
Can you hear me now?
Yes, we can hear you. Can you hear me okay?
Fine. Yeah, okay.
Nice
listen,
to
okay, so answering that question, I think that the modern buildings are really not fit for the future. So I think the move back to mixed mode will be important. It requires. Can you hear me?
Yes, we can hear you okay, Sue.
Okay. It requires going back to narrow footprints of buildings like they have in the Berlin planning ordinance, where they insist that you only have 16 to 18 meter maximum floor plates, so you can have central corridors with offices down the side or cross ventilation. What we've had is developers trying to make deeper and deeper buildings so you don't have any access. So I think we're going to have to rethink some of the way we plan the footprints of buildings too, to ensure they've got natural daylight and natural ventilation. Do you remember the ING Bank in Amsterdam, where they took a big deep plan building and they just blasted a new light well down the center of it and turned it into a naturally ventilated building? I mean, it's a lot of thinking, but I think home working is going to make people don't want to go to the office now. I've seen a number of surveys. People don't want to get into the lift to the 22nd floor with 10 other people anymore. Sorry. So I think it's a revolution. We're at the beginning of a revolution. Unfortunately, most architects are working with the blunt instruments of design models, which can't cope with natural ventilation well or thermal mass well, or they just churn out sort of industry standard commercial
footprints, and architects no longer know what an external wall does. How much mass do you need in a building? And I think that air conditioning engineers, the other big revolution we've got now is the move back to radiant heating and cooling. So engineers who've basically been trained to produce, basically fit in ducts and fans and Hevac systems that just push air around a building. I think that's going to be pretty long, you know, it's not the future. Sorry, I didn't really answer your question, Chris. I think we're on the edge of a revolution.
Yeah, thanks. Thanks very much, Sue. It was a comprehensive answer, and I think it did answer it reasonably well, or very well, actually. But you know, a comment from Shane Rogers there, who's actually a colleague of mine, who's our senior architect in our firm, and he's reiterating what you've been saying about the building regulations. They are out of touch. They're written by people who think that you know, living in a city is probably the way forward, and it's very, very different if you live in Thurso or Wick to living in Glasgow, Aberdeen, or Dundee. And the climates are very different, even over the short distance. You know, 300 or 400 miles in Scotland is a huge climate difference. You know, so I fully understand. Right, question or come from Kaiwan. Thank you for a great talk. I am curious about the results that indoor comfort was not found to be affected by relative humidity. However, theoretically, relative humidity affects sweating efficiency, and I personally feel uncomfortable when the air is both hot and humid. Why do you think that study didn't find the mediating effect of relative humidity on comfort?
Kai, that's a jolly good question. And I don't know if you know the work of Baruch Givoni and a lot of different people. Fergus has done some others. What you will find, Kai, that you're responding to when it gets hot and you've got quite high humidity there, you'll find that actually as it nears upper skin temperature, sort of medium skin temperature, 32, 33, 34, 35, then what you're feeling is you're feeling a lot of discomfort because of the temperature. Yeah, that's getting to be dangerous temperatures. And what have a look when you say higher relative humidity affects sweating efficiency. Obviously, I mean, Mike Humphreys always says 36.9 degrees centigrade with 100% relative humidity is potentially a lethal climate. Well, it is if you're sitting in it for, 24 hours or something. But with higher relative humidity, do a study yourself. Look at the actual temperature. I'm saying that you're feeling uncomfortable above 32 because of the temperature. And then get a meter like I've got here in my room. Check the relative humidity too. And it'll be very different in the morning, lunchtime, evening. But I think probably what you're really responding to is either insufficient movement of air over the skin to remove sweat, or just high temperatures. And I think you probably won't even feel that above 32 centigrade. Sort of below 32 centigrade, and what you're doing is getting hot and sweaty, and therefore you put the fan on, and that will remove that problem until you get to 35 and 35. So between 32 and 35, you just increase the airspeed over your skin, and that's fine. But just test the relative humidity and see whether you can actually tell what relative humidity you're in. Let's face it, I mean, with the amount of rain we get in Scotland, I mean, the relative humidity must be near 100% for a percentage of the year, but we don't keel over with it. Does
Okay.
that answer that? Okay.
Thank you. There are another couple of questions coming in there. Now, we've overrun the time quite a bit, but this is such a fascinating subject. I really don't want to just finish there. So there are a couple of questions. Firstly, we'll take the one from Chris again, University of Edinburgh, who says, if I may ask a second question, as relative humidity is a function of temperature, can we separate the two?
That's a very good point. No, you can't really. And that's what I say, it's temperature that you're responding to. What we do is we use absolute humidity in the studies. So relative humidity is a function of both, right? So what we do is in the analysis of the impact of water content in the air, we tend to use absolute humidity. Or let me say my students and colleagues do. Is that all right? Gary, I think you've turned off a...
Right, sorry, yep, there we go. Thanks. So we'll take one last question just from Shane, who's saying that hermetically sealed buildings are not the answer. And I think a lot of architects do realise that now. And asking, are you involved in the future development of this area with the Scottish Building Standards Agency?
I've been in touch with them over the years, but we have also, if you go to the Comfort at the Extremes website, in September, on the 5th and 6th of September, starting with a big party in Edinburgh Castle on the 4th, we've got a 2-day conference where we have the world leaders coming from America, from Austria, from Australia, around the world, from Japan, around the world, coming to look at the future of standards and air quality in buildings. So don't forget COVID, the real scandal about so many modern buildings where you cannot even open a window. We have this in Scotland, the Queen Elizabeth II Hospital. It's just like a tragedy because you've got such high clusters of COVID in a building where you cannot even, a hospital, you cannot even open the window, because the fastest way to purge a viral load out of a building or a pollution is to open the window and just, let it, put a fan in and make sure it you can purge it in minutes. And a hospital that has no opening windows I think is criminal. And we've got very high clusters. And we've got Stephanie Dancer is going to be talking about the COVID clusters in Scotland, Scottish hospitals in Lanarkshire, and bringing this home. So no, I mean, this is what I say, that the future has got to be, I think, trimodal buildings. So they talk about mixed mode, so you can run it in natural ventilation or with air conditioning or heating or cooling. But the third mode in the middle is the big new development, which is, there's all those environmental controls. This is work coming from California where they've done lots. You run a building in winter at a fairly low background temperature, like 18. Some people are perfectly comfortable in that, but other people will want additional heating. So you give them a small local heater. You heat the person, or in summer, cool the person. So you run it at quite a high temperature, but somebody who's rather well endowed and sitting in the wrong place might feel too hot. So you give them a desk fan or a cool chair or something that they call these personal comfort technologies. So the idea is you minimize, you don't heat or cool the building, you heat or cool people. And that's a third mode where you're using small, really energy efficient little things to heat or cool people who need it in the general background. So trimodal, naturally ventilated with no, that's your sort of thermoneutral zone of the building. And then when you need to heat or cool at the extremes, you probably put in your bigger systems, but then you run those intermediate ones on heating or cooling the person, not the building.
Well, that was a very full answer. Thank you very much, Sue. Right, I'm going to just draw to a close there because we've run well over time, but I really didn't want to shorten that because it was absolutely excellent. And I would thank everyone who's attended tonight for listening in. And I would remind you that the talk tonight has been recorded and they will be available on YouTube. Give it a few days just to get it uploaded, but you will be able to get the information that you seek from Sue's talk again. So thank you very much. And on behalf of everyone who attended tonight and also on behalf of the Scottish Committee, I would thank you again, Sue. And just very briefly, I would remind everyone that we will continue with our talks, and if you want to get in touch with the Scottish Centre of the Royal Meteorological Society, we can be contacted at scotland@rmets.org. And if you Google RMETS events, you will see that it's not just the Scottish Centre. There are lots of events from all the centres, and they're all really excellent. We really pride ourselves in the quality speakers that we have. So again, I would thank everybody for coming along tonight, and I would ask you to thank Professor Sue Roaf. Unfortunately, you won't be able to hear the applause, but thank you, Sue. So if I could just ask you, after everyone else logs out, we'll draw to a close here, if you could just hang on a few minutes and we can just thank you more formally. Okay, thank you very much, everyone. Right. Sue, thanks. That was really very inspiring, and you're obviously very passionate about the subject. And coming from a background, and this is what we do in life, it's of particular interest. And you know, Shane, our senior architect, who was on this and raised a couple of questions or made a couple of points, is also very passionate, as well as about a firm, that you cannot design something for London that's going to fit up in Thurso. It's when it comes to sustainability and climate, there are very, very different climate models out there for different areas. So yeah, it was.
So, you know, one thing I think is that the models are the problem. The models are just so crude and stupid. Actually, you're better off using a piece of paper and a pencil and putting your ideas down, building it up. You know, you use a model to maybe test 2 or 3 iterations of a particular design challenge, but you do your thinking. You need to think. If you're modeling, I've got a very good paper here. I'm going to include it. Oh no, that's happy hormones. Oh no. You're completely distracted the whole time. How do I draw this line? What color should that be? How do I relate to that? You're always thinking about the model, and it's distracting you from really deep thinking time. We need a lot of very deep thinking in design now.
Yeah, what is encouraging is that there are people out there who are looking at this very seriously. We do a bit of work in the Cairngorms National Park area, and the Park Authority are very keen on sustainability and having buildings designed that fit the community and the landscape they're in, using as natural materials as possible. So there are those who are very sympathetic, but it's not getting through to everyone. But with climate change, it's going to have to, isn't it? Really?
Yeah, and I tell you something, one of the real problems is the passive house movement. It's 1990s thinking from Bavaria. Faust comes from Bavaria, and they're rather they're really Luddite in a way. They say nobody can be comfortable at any temperature above 26 degrees centigrade. I mean, they really ought to get out more. But the idea that developers love it because you get chipboard mansions, you get lots of cotton wool and insulation, you've got no drafts, you've got no cold bridges, you've got put it in a plastic bag, lots of insulation, and then they put a machine in for ventilation in a greenfield site. You know, with that cost of that machine, cost you what, 12, 13,000. You could put solar hot water, you could put photovoltaics, you could put a battery, you can run that house on nothing. But most importantly is you have to have thermal mass in there. Because, I mean, what you do in the solar buildings, right? You take the sunshine from the day and you store it to the night, right? And where does that matter? It's like my house. I live in a wonderful house that's a very heavyweight. And so I've got a month stored heat in here. So the lights go out, the grid goes down, I'm safe, yeah? And so on the 7th of April, the first opening speech after the one about how bad is the climate going to get is by Keith Goff on how do you get a building that inherently stores energy in the mass or in a battery or something, that when the grid goes down, the building doesn't fail. And that's what he specializes in with his inverters and stuff. So, I mean, how many houses in Scotland, 2 weeks, sometimes 3 weeks, some of those houses, when the grid went down with the more extreme storms. So you've got to have thermal mass in there. This is what they did with the old traditional buildings, you know, that big, heavy fireplace in there that would give you a bit of resilience.
Yeah, I think you and I could debate this for quite a while, and I was fascinated by your point. I'd never actually heard that before, that we should be designing the comfort of buildings for the people, not the building.
Yeah.
You know, we had a class example of that. We designed our office and we built it 17 years ago, and we put in comfort cooling. And what we have now is we've got some staff who will put the comfort cooling on. Some people will then go and switch it off, and others will sit with an anorak on, while others are sitting with a shirt on. And some people have got a radiator, electric panel radiator under the desk, and I'm going through opening the windows. So the building was designed for the building, not for the people in it. We haven't cracked.
Yeah, no, but I mean, this is all most modern buildings. I mean, what I suggest for you, I mean, comfort cooling, is it overglazed? Why do you need cooling?
It does get very warm in the summertime.
Have you got big west-facing windows?
We don't have big windows, but we do have west-facing windows. The main drawing office has got a big patio door, first floor, and two or three windows facing out west. But the building does heat up quite considerably.
Yeah, but you know, that west-facing for Scotland, that's an absolute killer. Because is it first floor or ground floor?
First floor we are.
Yeah, I would put awnings above that. I was the RIAS judge, I think 2016, on the best building in Scotland, the Dolan Awards, right?
Yeah.
And we went round 16 different buildings, and I think there were 7 houses or so. And they all, it's the patio door mentality, but the one that's so beautiful, facing down the loch to the west, you know.
Yeah.
And they use it at weekends, and they've got the wall of glass down there. It's impossible. You know, that by the time they get there at the weekend, it's 38 degrees centigrade inside, 40 inside, because you've got that low summer sun. And, you know, you see, the thing is that with glass, if you get the closer, if you've got the high winter sun, you get less penetration. The thing with the low west sun, it just goes straight through.
Yeah. Anyway, so as I said, you and I could debate the buildings for quite a while, but we're obviously getting on in time. And again, I would like to thank you very much for your excellent presentation tonight. It really was interesting, and some good questions actually as well.
Yeah.
So normally, as I said, we would invite our speakers out for supper, but during these times.
Listen, I tell you what, I'll take a rain check.
Absolutely. Well, as you know, our meetings are usually in the university geography department in Edinburgh.
Yeah.
So I'm sure I will meet you next time we're in a face-to-face.
Okay. Nice to meet you, Stuart.
Yeah. Well, it's been really nice.
But do go on our website, www.comfortattheextremes, and get a couple of your lads to go, because it's going to change their mind.
Yeah, will do. Yes. Okay. Well, have a really good weekend.
Cheers. Yeah, and you. Should be nice and warm. Okay. Cheers. Thank you for being such a good chair.